Okay. I'm not sure I have the same book as you. Maybe. Who's the author of your book? Penny, DeManna, Waits, and Kennedy, or is it Larson, Hostetler, and Edwards?
I am not sure. I left my book at school today.
Okay. Well, in terms of problems, can you verbalize the problems?
Yeah.
Okay, let's do it that way then.
Okay.
All right, what's the first one?
On page 68.
I don't have your book, so I'm not sure I have your book.
Okay.
Let me turn to 68 and you tell me the problems and I'll see if, yeah, I might have those. What's the problem?
The limit of root 2 plus x minus root 2 over x as x approaches 0.
That's 63?
Number 54.
54. Yeah, I got root 2 plus x minus root 2 over x. Okay.
Yep.
Good. I do have your book, and it's Larson, Hostetler, and Edwards.
Okay.
Okay. Let's talk about limits for a moment.
Okay.
What is the limit of x plus 5 over x minus 3 as x goes to 4?
9.
Okay. So you're familiar with substitution.
Uh-huh.
Okay. What's the limit of 1 over x as x goes to 0 from the right? Have you done left and right-sided limits?
Yeah.
Okay. So what's that?
Would that be infinity?
Yes, very good. And finally, what's the limit of x over 1 as x goes to 0?
Does not exist.
No, that's 0.
Oh.
Okay. Usually you get your does not exist. Does not exist basically means that the limit from the left is not the same as the limit from the right. Okay. Well, if we look at that previous problem, oops, hold on. Let me erase this one. My eraser isn't working. What is the limit of this one as we approach 0 from the left?
Negative infinity.
Since negative infinity is not the same as positive infinity, then if I said the limit as we approach 0, that does not exist.
Oh.
Because the first thing that has to be true for a limit to exist is it has to be the same from the left as it is from the right. Okay? And negative infinity is on the other side of the number scale compared to positive infinity, so you can't get much further apart than those two. All right, so you know how to do numbers over numbers. You know how to do 1 over 0. You know how to do 0 over a number. All of those are easy. The ones that are tough are 0 over 0.
Yeah.
Take the most basic one they work with. What's the limit of that? First thing you notice is that it's 0 over 0 on direct substitution. Okay, 0 over 0 is called indeterminate. In other words, it might be a number, might be 0, might be infinity. It could be anything. We don't know what 0 over 0 is without doing more work on it. Okay? All of the tough limit problems they give you are all going to be 0 over 0 when you first substitute.
Yeah.
So there's basically 3 or 4 techniques to handle 0 over 0. The first and most important one is factoring. So if I factored the top here, what's that factor into?
X plus 1 and x minus 1.
And then if I put the x minus 1, I can cross out that with that. And this thing is actually the same as x plus 1. And what does x plus 1 do as x goes to 1?
2.
So that would be the limit of that. Even though we started with 0 over 0, it went to 2.
Okay.
Okay. Now, 54 is the second technique. And whenever you see radical signs, know that you're probably going to have to use this second technique. In other words, I can't factor this, right? And let's see, this is a limit as x goes to 0. So I'm going to get 0 over 0, right?
Yeah.
Okay. Well, if I can't factor it, the very second technique I look to do is to multiply top and bottom by the conjugate of the most complicated part, which is the top here.
Mm-hmm.
So I'm multiplying both sides, or top and bottom, by the conjugate of the top. Well, you know what the conjugate of the top is?
Root 2 plus x plus root 2.
Yeah. In other words, it's the same two terms with the opposite sign. And since I have to multiply the bottom by the same thing, because I can only multiply a fraction by 1 without changing its value, well, here's my 1. That's 1 right there. So I can always multiply any fraction by the number 1. Okay? Now, the beauty of multiplying by the conjugate is you don't have any middle terms. In other words, if I multiply a minus b times a plus b, I get a squared minus b squared. Think difference of perfect squares.
Okay.
Okay? So when I'm multiplying the top together, I know that there's not going to be any middle terms. There's not going to be any ABs or BAs. They both get canceled always when you're multiplying by the conjugate. That's why it's such a beautiful technique. So when I multiply the tops together, the first term is a squared, which is 2 plus x, right?
Yeah.
And the last term is 2. In other words, it becomes this squared minus that squared. That's what you always get when you multiply by the conjugate. And bottom is x times, and never worry about multiplying this out. You don't have to. In other words, always leave that in factored form like that.
Okay.
Now notice what happens. The 2's cancel in the numerator, and I'm left with just x. Now I can cancel the x that's in the numerator with the x that is in the denominator, leaving a 1 in the numerator. And now the whole thing turns into 1 over square root of 2 plus x plus square root of 2. And I'm taking the limit of that as x goes to 0. What is this limit?
1 over 2 root 2.
Yep. Now, this not being trig, they want us almost always to rationalize that. You're not going to see this answer in the book. If you had answers to the even ones, that wouldn't be it. Why? Because we have an irrational denominator. So never give, I shouldn't say never, because in Trig, the thing that makes the most sense is to forget all about rationalizing denominators and just leave it like this. It's the most intelligent thing I've ever heard a Trig teacher say. I had a student and he said the teacher told him, do not rationalize your denominators. It's not worth the effort in Trig because you're constantly flipping. In other words, you're frequently taking the reciprocal. Remember that cosecant is the reciprocal of sine, and so if you rationalize everything, you end up having to rationalize it twice a lot of times. But since this is calculus, not trig, let's rationalize that. How do I rationalize that?
Multiply by root 2 over root 2.
And what do you get?
Root 2 over 4.
And that's your answer. That's what the limit is. Okay. Are you doing these sequentially? 55 next?
Sure.
Let's do 55. And then I noticed that on 57, there's another technique that you have to use.
Okay.
Let's do 55 to make sure that you can do it the way I just showed you. Again, we got radical signs, which means we're probably going to have to use the conjugate because I don't see any way to factor this. And this clearly is going to be as x goes to 4 because that's the only thing that's going to give you 0 over 0.
Mm-hmm.
Okay, so what's the next step? In other words, the first step is always substitution because you're not always going to get 0 over 0. They might, give you a test where the very first problem is not 0 over 0. It's like 2 over 7 or something. So substitution is always the way you want to start. But once you get 0 over 0, then what should I do here?
Multiply by root x plus 5 plus 3.
Top and bottom.
Mm-hmm.
What's that give you in the top?
X plus 5 minus 9.
And I'm going to write the bottom this way. In other words, the last thing in the world I want to do is try to multiply these together in the bottom. That's just a waste of time.
Yeah.
First of all, it's hard to multiply those two, but even if you could, you wouldn't want to. Now notice what the top becomes. X minus 4.
Mm-hmm.
Now what?
Now the x minus 4's cancel.
You're left with?
1 over root x plus 5 plus 3.
And what does that go to as x goes to 4?
Root 9 plus 3.
So it's 1 over 6.
Yeah.
In other words, it's 1 over the square root of 9 plus 3. So it's 1 over 3 plus 3. That's its limit.
Mm-hmm.
Okay? And so even with this technique of multiplying by the conjugate, I still end up, I guess I don't have to factor anything, but I've got to get rid of the numerator. The numerator usually cancels with something in the denominator once you've done multiplying by the conjugate.
Mm-hmm.
And then it turns into no longer being a problem of 0 over 0. Now, the third technique, are you supposed to do all of these or?
He didn't really assign any, just getting ready for the quiz tomorrow.
Okay. But you have had problems like 57?
Yeah.
Okay, let's do it. Remember, the first technique is factoring. The second technique is multiplying by the conjugate. And this technique is actually adding the fractions together.
Okay.
Using algebra. Okay. And clearly, well, upon direct substitution, I get 0 over 0.
Mm-hmm.
And so I don't really want to multiply by the conjugate. Not sure that would help. Let me think for a second. I multiply by the conjugate, I don't believe I can cancel anything out. I don't know. It might work, but that's not the technique I would use. In other words, I'm looking for a common denominator, and I'm going to operate on the numerator. So what's the common denominator going to be?
3 plus x
Times 3.
Oh, yeah.
That's going to be the common denominator. This is the way I kind of do these when I'm trying to find, when I'm adding fractions or things like this, I write it like this, okay? In other words, I found my common denominator, so I know that's going to be in the denominator. Now I have to figure out what goes here. What goes here? If you can see where I'm pointing, right there.
So that would be 3.
Okay, and what goes over here?
3 plus x.
Okay. Now I can operate on the numerator like that. And that, the 3's cancel, and I'm left with x over 3 plus x times 3 all over x. Okay? Now what do I have to do?
Multiply the bottom x by the reciprocal.
Yeah, the way I prefer to think of this as I'm dividing by a fraction. I'm dividing a fraction by a fraction, so I'm going to flip the bottom and multiply. In other words, this whole thing is the same as multiplying the numerator by the reciprocal of the bottom, which is pretty much what you said. And actually, you put it more mathematically correct. But this is what I'm going to do. Okay? Now the x's cancel. Now I'm left with 1 over this. And what does that go to as x goes to 0?
0.
Sorry, what?
Oh, no, not 0. It goes to 1 over 9.
Right. That's how you do that problem. Now, I'm a little curious. What would happen if we did multiply by the conjugate? Let's see. I've always assumed you have to do these the way I just did it. But what if we multiply by 1 over 3 plus x plus 1/3, top and bottom? In other words, you might be able to use the conjugate always. And then the top is this term squared. So it's 1 over 3 plus x squared minus 1/9. Yeah, that doesn't work quite as nicely.
No.
So using the conjugate on this doesn't work so nice. Far better to just treat these as two fractions and go ahead and find a common denominator. And that's actually a common method with calculus, is to find that common denominator. And that's one of the things that makes calculus hard, is because these always are fairly difficult algebra.
Yeah.
In other words, that's not an easy algebra problem, even though once you get used to subtracting fractions with variables or adding fractions that have variables in them, It's not that hard. But so the only place that I always know you end up using the conjugate method is when you have radical signs. Because if I got radical signs, there's no way I can subtract those two fractions. But if they're in this format, I can. And it's better to go ahead and just operate on the fractions. So that's our three methods. Now, have you had trig functions yet?
Yeah.
Okay, so you've been told that this is equal to what?
1.
And notice that's also 0 over 0. And there's no easy way to prove that that's equal to 1. Hard problem. In chapter 8 of this book, you'll get L'Hopital's rule. And L'Hopital's rule actually has a rather easy way of solving these problems that have 0 over 0. And that's you take the derivative of the top, and you take the derivative of the bottom, you reevaluate it, and you end up, in this case, getting 1. But you have to have differential calculus before you know how to take the derivative, and they need to teach you this limit before you get to differential calculus. So it's a little bit like having the chicken and the egg. The only way they solve it is to say, memorize that one and this one. What's that go to?
0.
Right. And if you memorize these two, then you will be able to do problems like this. Notice this also goes to 0 over 0. How would I do this problem?
Would it just be equal to 5?
It would, but the way we get that is I'm going to multiply top and bottom by 5. There's the top multiplied by 5. There's the bottom multiplied by 5. Now, I can see that that has to go to 1. It doesn't matter if it's 5x over 5x or the sine of 100x over 100x. As long as this is the same as this, then that limit goes to 1. And since that limit goes to 1, and I'm multiplying it by 5, then that whole limit goes to 5.
Okay.
Okay. And you've had trig problems with...
Yeah.
Okay, let me find some others here. 68. What does that go to?
I'm not sure. I don't have the book in front of me.
Oh, sorry. Got it.
Sorry. It's in my locker.
No, that's fine. You don't actually have to bring it if you know the numbers that you're supposed to do, because I'm always going to have my book. Again, this goes to 0 over 0, as they all will on this page.
So that would go to 0.
Because this part goes to 0, and no matter what this number is, a number times 0 is 0. Okay. You find a little harder. These can get kind of hard, especially you need to really know your trig identities a lot of times. Although not yet. And of course the limit as x goes to 0 is going to be 0 over 0. So how to solve this? Think of separating it out. In other words, this is the same as sine x times 1 minus cosine x all over 2x times x. Okay? Well, I may not immediately know what that does, but I do immediately know what that does. What's that go to?
0.
Which means the whole thing goes to what?
0.
Yeah, because this is going to go to some number. It turns out this is going to go to 2, right? The thing I have circled on the left, in order to figure out what that went to, I'd have to multiply, excuse me, this goes to a half. In other words, I got to multiply the top by 1/2, got to multiply the bottom by 1/2, and then I've got 1/2 of sine of x over x times 1 minus cosine x over x. So I know this goes to 1. So this whole thing goes to 1/2, but since this goes to 0, the whole thing has to go to 0, and I really don't need to do that part of it. The only time I might need to do the left part is if it goes to 0.
Oh.
Because there's some indeterminates. 0, well, 0 times 0 is not indeterminate. That's 0. So even if this thing with the check mark were to go to 0, I've still got 0 times 0. So I'm done as soon as I separate that out and know that that goes to 0. I don't even have to give any attention to the left, because whether the left goes to a number or goes to 0 matters not.
Mm-hmm.
Maybe if the left, the numerator went to a number and the denominator went to 0, then I would have 0 over 0 still, and I would have to do something with it. You're going to learn later that there's not that many indeterminates. There's this, there is this, there is this, and there is this. All of those are indeterminate. We don't know what the answer is.
Mm-hmm.
Okay? How about this?
Mm-hmm.
What's this go to? What's that equal to? Not indeterminate.
Can you have negative infinity?
Yeah, you can definitely have negative infinity. That's just all the way to the left on the x-axis. But in this case, I'm adding it to another negative infinity, so I get minus 2 infinity, and that's always minus infinity.
Okay.
In other words, 3 times infinity is just infinity. 17 times infinity is just infinity. Okay? So, in other words, this is indeterminate because infinity is not a number, remember. It's a concept. So if I take infinity minus infinity, I have no idea what I have. But if I take an infinity and add an infinity to it, well, now that's 2 infinities, which is the same as infinity.
Mm.
So it's not always indeterminate just because there's infinities involved and stuff. These are the only indeterminants that I know for sure. The 4 that I show right there. All right, let's go back to trig here. Let me see if I can find a more difficult one. Yeah. Cosine. And, I mean, maybe I don't need to look for more difficult ones. I don't know. How difficult is your test going to get?
He'll probably put some pretty hard ones on there.
Okay, then let's do these. Because the polynomials, I think you can do all of them with those three techniques that I showed you. Either factoring, multiplying top and bottom by conjugate, or operating on the fraction that you see by finding a least common denominator. With trig limits, they can be quite a bit harder because we don't know what tangent of theta over theta is. Okay.
Yeah.
And I don't know what cosine of theta. Yeah, I do know some of these. This has got to be as theta goes to 0. So the first thing you know is tangent of theta. Tangent of 0 is 0. So I do have 0 over 0, even though the cosine of 0 is 1. Okay. So I got to turn this, I got to do something with it because immediately on substitution I get that. And what can I do? Well, let's use the trig identity for tangent. What is that?
Sine over cosine.
Okay. So instead of tangent, I'm going to make that sine over cosine. Now the cosines cancel, and I end up with that. What's that limit?
Sine over theta.
Sine of theta over theta as theta goes to 0. What's that limit? It's the one they make you memorize.
Oh, 1.
Right. The only two that I know of that they're just going to give you and say memorize are this one and then the 1 minus cosine theta over theta. Okay. Let's go back and look at this. This must be hard, otherwise I don't see why it's number 71. What can I do to this?
Can you separate it out?
Yeah, think factoring. Basically what we're going to do is factor the top. Well, when I factor the top, it becomes sine x times sine x, right? So that's the same thing. And now I know what the first sine x goes to is 0. I know that goes to 1. 1 times 0?
0.
0. So I still don't know why this is problem 71. This is easier than the earlier ones on this page.
Yeah.
Here's one. Tan squared of x over x.
Sine over cosine.
Yeah. So it would be sine squared of x over cosine squared of x times x. Let me write that x there so it's not confusing. So that's the first step. In other words, with all these trig functions, since the only two they've told you are the sine and the cosine one, then anything that's not sine or cosine, we got to make into sine or cosine. In other words, I don't know what the tangent of x over x is as x goes to 0. But I can always work with this. And then again, now what? Let's see what happens if I do this. That works because now I know that that's the same as that multiplied by that. What's this one go to?
1.
And what's the one on the right go to? Just by direct substitution.
0.
No? Well, yes, it does, but it's 0 over 1.
Right.
Okay, so I'm multiplying it by 0 over 1, which is 0. Anything times 0 is 0, so the whole limit goes to 0.
Mm-hmm.
Okay. All right, let's try this one here. This one looks hard. I'm going to change it to theta instead of as theta goes to pi. Well, remember that a number, in other words, what's the secant of pi? Secant is the reciprocal of which trig function?
Cosine.
It's the cosine of pi.
-1.
Yeah. So what's the secant of pi?
1 over -1.
Which is -1 also. So by direct substitution, I get pi times -1. In other words, this is the easiest one we've done yet because it does not involve a indeterminate. Now, I can make it a lot tougher by making this cosecant. Notice why it's a lot tougher now. And there's one other indeterminate I just realized. And no, this is not indeterminate either. In other words, what's the sine of pi?
0.
So what's the cosecant of pi?
1 over 0.
Which is?
Does not exist.
Well, we'll call it infinity.
Yeah.
As long as we approach pi from the right side, it's infinity.
Mm-hmm.
Okay, and this is pi, so what's pi times infinity equal to?
Infinity.
Yeah, they're going to say undefined.
Okay.
And that's fine. In other words, it actually is kind of the cosecant of pi is really not defined because it's positive infinity if you approach it from the right, but it's negative infinity if you approach it from the left. In other words, the cosecant curve looks like this with vertical asymptotes at pi. In other words, your vertical asymptotes are always wherever sine is going to be 0. Sine is 0 at 0 and sine is 0 at pi. So cosecant is going to be infinite. But notice, if I said to you, what is the limit of cosecant of theta as theta approaches pi, what's the answer? Well, let me put that a different way. As theta approaches pi from the right, look at the graph. What is it?
Infinity.
It's negative infinity.
Oh.
Right?
Right.
In other words, we're down here at negative infinity if I approach it from the right. If I approach it from the left, what is it?
Infinity.
Correct. Since positive infinity is not the same as negative infinity, then if I ask you what is the limit of the cosecant of theta as we approach pi, like that, that has to be a does not exist, because the limit is not the same from the right as it is the left. And I can't really say it's infinity either. It just doesn't exist. That's the number one rule of limits. It's got to be the same from the left as it is from the right. Okay? Since that is a does not exist, and I'm multiplying it by pi, that's got a does not exist also. So the answer to the problem that I gave you was does not exist. That one wasn't in the book. It was theta times secant. And secant doesn't go to infinity as theta goes to pi. It goes to -1, just like you said it did. All right. Let's see. Well, I'll give you some more trig. Yeah, let's do this one here. Give you some trig where everything is not in sine and cosine. And here I'm taking the limit as x goes to pi over 2. So the top is 0. It's the cotangent of pi over 2. Zero also. Okay, so direct substitution, you have 0 over 0. So what should I do to this?
Change cotangent to cosine over sine.
Yeah. So cosine over sine, flip and multiply gives me sine, right?
Yeah, because cancel.
So it's the sine of x as x goes to pi over 2. What's that do?
That is 0. I mean, 1.
This is the sine curve here. And this is pi over 2. So as I approach pi over 2, I'm going to 1. This point right there. Okay. And let's have a look at this one. Again, 0 over 0. What do we need to do to turn this into something that I can evaluate?
Multiply by
what do I need to turn the denominator into? 3t.
Yeah,
Right?
Mm-hmm.
So what do I need to multiply the denominator in order to turn it into 3t? Right? So
yeah.
if I multiplied the denominator, I got to multiply the numerator. Now I've got 3/2 sine of 3t all over 3t. In other words, when I do the bottom, it turns it into 3t. And now I know that that is 1. So that whole limit is 3/2. This one's hard. This one they even have to give us a hint. You know they're hard when they don't let you just tackle it. They have to tell you something else. And I'm glad they do, because right offhand I'm not sure how I would do this. fact, I haven't looked at their hint yet. But if I'm looking at this, I get 0 over 0. Can't really turn the bottom into 2x.
Yeah.
I'm guessing that they're going to use the double angle formula here. Let me see what their hint is. Oh, I see. I see what they're doing here. I need to, first of all, multiply the top by 2x, top and bottom. I can do that. And now notice that I've got that, which I know goes to 1. So I can now write it as 2x over sine of 3x times 1. With me?
Uh-huh.
Okay. Now 2x over 3x is still 0 over 0, which is indeterminate. But if I can turn this into 3x over sine of 3x, that limit has to be 1 also. In other words, it's not just sine of x over x that goes to 1. It's also x over sine x that goes to 1. Okay, and so in order to make this look like x over sine x, I got to get this to 3 halves, or to 3x. So again, I have to multiply the top by 3 halves and the bottom by 3 halves, like that. Now I've got 3x over 3 halves sine of 3x times 1, or if I want, I'll go back and write it like this. In other words, I got my original turned into this now.
Okay.
Okay, I know that that is 1. That goes to 1. What's this whole thing go to?
3 halves.
Nope. Remember that 3 halves is in the bottom now.
Right, so it's 2/3.
2/3. I got to flip it. In other words, 1 over 3 halves is 2/3. Okay. Well, that's an interesting problem. That's the first one we've come across where I had to multiply the top and bottom by not just a number, but a number and the variable. I had to multiply it by 2x top and bottom. And then on the right, then I multiply by just 3 halves. But the first step is to multiply by the variable. I didn't see that when I first looked at it. I wonder how long I would have had to look at that before figuring it out. A lot of times these things just you kind of got to do some problems to lock it in your memory as to how to do these kind of problems.
Yeah.
Let's do one more tough one. And then we'll leave the trig at this one and go back and look at some more polynomials. Just because I can't imagine they're going to give you anything tougher than this. In fact, I can't imagine they'd give you anything tougher than the last one we just did.
Yeah.
And this is the limit as x goes to pi over 4. Well, we know the tangent of 45 degrees is 1. So the top is 0. Sine of pi over 4 is the same as the cosine of pi over 4, so the bottom is 0. So we get the indeterminate. Now the question is what to do with it. They don't give us any hints on this.
So first change the tangent to sine over cosine.
Yeah, that'll work. And then handle the numerator like it's a fraction. The problem is then I'm going to have two terms in the denominator. When you have two terms in the denominator, you cannot flip it and multiply. In other words, I can't multiply the numerator by 1 over sine x minus cosine x. That only works if you have a single rational quotient in the denominator. So,
Can we pull it apart?
well, I can't separate it into the two fractions you might think I could. It's not 1 over sine x plus tan x over cosine x. I was thinking multiply both top and bottom by the conjugate of the top, because that'll give me 1 minus tan squared. But 1 minus tan squared doesn't have a trig identity, so that's not going to work either. So I think your method is the best way to do this. Let's see what happens when I do it this way. That's the numerator. Combine that, what do you get? In other words, find a common denominator.
Cosine x.
Okay. What's 1 turn into?
Cosine x over cosine x.
Which means that whole numerator becomes this. Right?
Mm-hmm.
All divided by sine x minus cosine x. You know, I actually can flip the bottom and multiply.
Okay.
This is an odd one. No, it's an even one. That's too bad. I wouldn't mind checking the answer on that. Actually, I can do limits on my Wolfram Alpha. Are you familiar with Wolfram Alpha?
No.
It's a website that is, it's a great calculator, an online calculator. If you ever find yourself taking a test without a calculator, without your calculator, and they allow you to use one, and you have your cell phone, just go to Wolfram Alpha, and that's a great calculator. It's great in the sense that it tells you the zeros of the function automatically. You don't have to trace. Is your regular calculator an Inspire or a TI 84?
TI 84.
Okay. I think that I actually can do flip and multiply. In other words, if I put a 1 under that, I can flip and multiply it.
Okay.
Yeah. Which means that the problem becomes this. And what's the difference between the top left numerator and the bottom right denominator?
It's cosine minus sine and then sine minus cosine.
So what is that? What is that divided by that alone? It's minus 1. A minus B over B minus A is minus 1. Notice why. I can write B minus A as negative A minus B, like that. And A minus B over negative A minus B is negative 1. So normally when you're turning something into 1, you need an identical numerator as you have denominator. The one exception to that is when you have A minus B over B minus A. Well, that's what we're looking at. We're looking at A minus B over B minus A, so I know that this part of it is negative 1, just algebraically, without even considering the limits. Okay. And so now the whole thing turns into minus 1 divided by cosine of x as x goes to pi over 4, which becomes, what's cosine of pi over 4?
Root 2.
It's actually root 2 over 2.
Right.
Or it's going to be easier if we use 1 over root 2, the unrationalized one. In other words, if you look at the triangle, the 45-45 triangle that they've taught you for 3 years, the unit dimensions are that. So if I said, what's the cosine of 45 degrees, you'd say 1 over root 2. And that actually works better here. If I do 1 over root 2 and flip and multiply, my answer is minus root 2, no rationalization needed.
Aha.
If I were to go to the trouble of rationalizing that and making it root 2 over 2, now when I flip and multiply, I got an irrational denominator again, and I got to re-rationalize it.
Yeah.
So I'd have to do 2 rationalization processes instead of none. Doing it this way, I had to do none.
Okay. That makes sense.
Negative root 2 is the answer. Why was I confused about that? I guess it's because of this. If I have something like 3/4 divided by 1/3 minus 1/4, I can't just flip the bottom and multiply because the bottom is 2 different fractions. I've got to combine those fractions before I can flip and multiply. And 1/3 is 4/12. 1/4 is 3/12. So this whole thing becomes 1/12. Now I can flip and multiply.
Oh, yeah.
And I'm fine. But I couldn't do it in the start because I had 2 fractions.
Mm-hmm.
Whereas in the problem we just did, we don't really have 2 fractions in the bottom. I have 2 terms, sine minus cosine x. So I guess I can flip that and multiply as long as I flip the whole thing and make it, sine minus cosine x over 1.
Yeah.
Ooh, you know what? I think when I flipped that, I did it wrong. I think I made a mistake. Let's see, that's the numerator. No, I did it right. I did it right. Yeah. The key to this problem is recognizing that divided by that is -1.
Okay.
I have -1 over cosine x, and the moment you get something other than 0 in your numerator, you got the problem solved.
Mm-hmm.
Because the only difficulty is going to be if you end up with 0 over 0. Right? In other words, the moment I get that -1 in my numerator, well, I know I'm done. I just have to figure out what the bottom does. If the bottom goes to 0, then it's undefined. If the bottom goes to some number, then you have your answer.
Mm.
Okay. I guess we can stop there.
Okay.
You good to go, you think?
I think so. I think I'm ready.
Like you know these pretty good. I expect you'll do pretty good on that test tomorrow. Just remember all these little tricks.
Yeah.
And I don't know, did you know how to do these before this session, you think?
A little bit.
Maybe you could do the polynomials, but maybe not the trig functions so much.
Yeah.
This might be one you want to review before taking your test.
Okay.
Now, I think, let's see, I got another session at 7 and another one at 8. The question is, can I get this uploaded before you go to bed tonight? I can probably get it uploaded around 7:30. So if you want to review the recording of this, long about 7, did you got my email that showed you how to find the file?
Yeah, I did.
Okay. That's what you'll do, and it'll be the top one on the list, but because yours is the only one I'll process just so I can get it up there tonight, but it'll have your initials, BS, along with the date 01/25/17. So look for that, but it should be the very first file that's listed on my channel.
Awesome.
But after 7:30.
Okay.
Sometime between 7:30 and 8. That's when I'll have time to upload it. All right? All right, Brianna. Thank you much. Talk to you next time.
Alrighty.
All right, bye-bye.
Bye.